Welcome to another video on the solution for Applied Electronics 2022-2024 academic year. So we stop at question 30. We continue from question 31. Okay. So we have a preamble. Question 33 to 35 refer to the silicon transistor circuit shown in figure 2 below. We have beta DC is given as 120. Now, the first question, 31, the value of what? IE. So we look at this circuit diagram, which is here. We have to try and find IE, which is the emitter current. So to find IE, you can see here that first, for me to be able to find IE, right? I can find IE by using what our knowledge by trying to find the circuit here, right? We know IE, we are given beta DC. Beta DC is going to what? IC over IB. Okay. And once I know my IB, I can get what? IE, right? We can get IE. Now let's try and get IB in that case. So once you know IB, I can get IE. IE is going to IB plus IC. So let's try and get IE. So based on this here, we apply Kirchhoff voltage law to this loop that we have. You can only loop 1. And for loop 1, Kirchhoff voltage law to loop 1. And then what do we get? We are going to get here, this is the voltage of VBB, right? We are looking at clockwise direction. So I can write VBB moving clockwise. So here the voltage across RB, here we call it VB. Then from there, because we have been told this is a silicon transistor, that means here we have what we call VBE. So we can write minus VBE, which is going to be 0. So with this, we substitute with what? The voltage across the RB is going to what? Meaning the base current IB times what? RB. So if you make IB the subject, we get this equals to VBB minus VBE over what? RB. So we just do the replacements. You can see here we have 3, VB 3. Then when it comes to what VB is 0.7, and then we divide by 10 kilo ohms. So we bring this one, that will be 10 milli. 10 is power 3. That will be milli. So we just have 3 minus 0.7 divided by 10. So I get 0.23, right? So here is 0.23 ounce. Okay, so we've gotten IB. So based on this, see that I can find IC using this formula. So IC will just be equals to beta DC times IB, which is beta DC is given to be 120 times 0.23 times 8 power minus 3. So this one times 120. So we get here to 27.6 milliamps. Right. Now that we know this, then I can find IE. IE will just be equals to 0.3, the sum of this. So I add this plus 0.23. .23, and then we get this, right? 0.23, and then that is going to give us 27 milli, 27.83 milli. Okay, so we get something of this nature. Where did I make any problem that okay. Beta. Beta is 150. Why is it written 120? So here there's a mix here. Beta is actually 120, 50. So if I take here, meaning here was supposed to be, there's a mistake in this. This way is supposed to be 50. So we're supposed to have 50 times 0.23. That will give us 11. So here should be 11.5. So that once we come and do the addition here, so 11.5 will now be plus 0.23. So that will be 11.73 minutes, which is just going to be close to 10 power minus 3. Yeah, that's just going to be what 0.0173. So it's going to be what D. Our answer is going to be D. Now the value of VCE. So how do we get VCE? VCE is here. This is our VCE. To find VCE, we can apply Kirchhoff voltage law to this one. We call it loop 2. And in that case, loop 2 is going to be equals to, let me clean this. So we have loop 2 here. And then with loop 2, you can see that again we are moving this time anti-clockwise. So I can have VCC minus VC minus VCE. VCE is here, right? This is our VCE equals to 0. So based on this, we are interested in VCE. So what do I get? VCE will be equals to, I know VCC from this equation. Where is the value of VCC? The value of VCC is not clear. I can't see it here. I can't see VC. Right? I cannot see VCE, VCC. It's not giving. Is it a mistake or here or something? But I think it's probably 5 or something, right? VCC here is not giving. So what do we do for VCE? Okay, VC here, the value is not giving, but let's assume it's, I don't know, probably 5 or something. If you assume VCC to be 5, so I have 5 minus VC here, which is going to be equals to, meaning the resistance, which is 1 kilo, times the current which we got was what? Remember I got 0.23 times 50. That will be 11.5 and 0 power minus 3. Now we just have 5. So this will cancel. So I get 11.5. This is probably around 10 or so. Here, this question, the VCC is not given. I don't know why it wasn't given. So based on this, if I'm using this to be 10, so 10, it can't be 10 because here we're already doing this, right? And based on what we are getting here, if this is going to be 11.5, so if you take 11.5 plus, okay, here they even wrote minus. So meaning this is probably 10. Let me assume this is 10. But I will just do it like that. 11, 10 minus 11.5. That will be minus 0.5. So I'll put it to be what B. Now the value of what VCB. So to get VCB as for this, I mean, it's going to be the collector base voltage. It's actually going to equal to what VCE minus what VBE. So when it comes to VCE, this place here, the voltage here, is going to be the sum of what the voltage here and then this voltage. So you get VCV to equal. So I can write here to be minus 1.5 minus 0.75. So meaning minus 0.75. We get minus 3. So this one also become B. Okay. So that is for the question 33 as well. Now moving to question 34. Which of the following electronic device can better be used as a switch? So when you talk about a device can be used as switch, it's going to be a thyristor. So we have C. So this is going to be C. The thyristor consists of what? 4 differently doped silicon, right? So the answer is going to be 4. A. Which of the following thyristors is the most commonly used one in the industry? It's going to be silicon control rectifier. So the answer is A. A thyristor conducts current only in one direction. So here we can say true, and that's always behave like this thing. True. The gate of a silicon control rectifier is connected to the P-type layer that adjoins the cathode, right? So we have, for example, this is our, let's say, P and P. So the gate is here. So it's the one that here is the cathode. And then I have here been the anode. So this one, say, silicon is widely used to make thyristors because I can handle current and voltage required for high power application through I is lighter than germanium. That's not the reason. Then we have, okay, if you compare to that, then germanium is lighter. Then I is because it's cheaper, right? It's because of I and C. Because it's can handle the same cheaper. Then for turn off a thyristor, to turn off a thyristor from its conducting state, the current flowing through it must be reduced below the holding current, right? The holding current. How many modes of operation occur in thyristors? We have 3. We have the reverse blocking mode, the forward blocking mode, and then the forward conducting mode or conduction mode. Then we have question 42. That is a minimum current that must flow through a thyristor before it can remain on the conducting state after the gate current has stopped flowing. It's going to be the latching current, right? That's the minimum current that you need to flow through your thyristor in order for it to be in the conducting state. We have 43. If the silicon control rectifier triggers near 20 degrees of a positive half circle, there's going to be 160 degree of conduction because the total conduction is 180, right? You have 180 degrees. So if you trigger 20, mean you have 160 degree conduction. There is 0% conduction if a near negative circle is being triggered. It's going to be true, right? There's going to be true here. If you trigger this, and there's going to be, if you are in the negative, you get 0. In the forward blocking region, the thyristor is said to be forward blocking, meaning the thyristor is still in the off state. When the thyristor is in the forward conduction region, it is regarded to be in the A conduction mode, right? When you are in the conduction mode. All these statements are always ways of turning a thyristor off, except we have here by increasing the circuit resistance, so that will turn off a thyristor. By reducing the anode cathode voltage to turn off a thyristor. C, by increasing the anode cathode voltage. No, this will not, so that will be the answer. By reversing the polarity of the anode cathode voltage, it will turn off a thyristor. So the answer is C. 48. A silicon control rectifier can be divided into a 4 3-layer device, right? 4 in the sense that you have 4 differently doped layers, and then 3 we have from the number of terminals or device we have, because we have the gate, then the cathode, and then the anode. Question 49. A thyristor can be represented by B here. No, not here. 2 volts. If it no, it can be represented by 2 bipolar junction transistor equivalent arrangement. So the answer here is A. The gate of a silicon control rectifier is connected to, this is repeated, so it's going to the P type that adjoins the cathode. So we have C. Effect of feedback on sensitivity is minimum in closed loop. When you are closed, and then sensitivity is going to be reduced. When voltage feedback is applied to an amplifier, its input impedance. Here we are talking of voltage feedback. Is applied to an amplifier. Its impedance is going to increase, right? The input impedance will increase, so it's B. Negative feedback is employed in amplifiers, right? We employ these amplifiers. In a negative feedback amplifier, series mixing tends to, when you have series, we are going to have an increase in the input impedance. So we have A, increase the input resistance, which is the same as impedance. An amplifier with a negative feedback, I control the gain, I reduce the noise, I increase phase distortion, I4, IV rather nonlinear operation. So here is going to be what I, meaning the first one control the gain and then reduce the noise. So we have C. All right. What is the main purpose of an amplifier? A, to reduce the power in the signal. No. So we can, if we were to control the power, no. To distort, it's going to be D, to increase the power in a signal without distorting it. So it's D. Feedback amplifiers are closely linked to which control system? So when we talk about feedback, we are talking about closed loop systems. What term refers to a decrease in signal voltage? So when there's a decrease, you can refer to attenuation. So the answer is B. Then the last question, which we'll be looking at, is which type of feedback connection involves tapping off some output current? So you tap off some output current. Here you can see that it's going to a D, right? Because here, when you have current shunt, you have the output being current, right? And then your feedback into your system is also current. So I mean, you are tapping on this. So this is D. Now we continue with the rest of the question in the next video. Bye bye.